So thanks for coming up. This is going to be the best math talk you've ever heard. So my name is Stephan Jou. I'm the CTO of a company called Interset. You've never heard of it, but we're in cybersecurity. But I actually spent a lot of time at IBM. So I built 12 IBM products and Cognos, all in the analytics space. Everything from data mining, so not your type of mining, but data mining, neural networks, predictive analytics, SPSS, part of Watson. That's all the stuff that I've done. One thing that's very important to realize is that I'm not in sales. I'm not in marketing. So I'm not going to be as well-spoken or as good-looking as Dirk, but you can totally trust everything I say. So it's okay. It's okay. Have I mentioned I'm not at IBM anymore? Okay. So what do I do? So I have a lot of opinions on data science and big data analytics, and I want to spend a little bit of time trying to demystify it a little bit. I want to help inspire you to think of new use cases on what we can do with all these really cool technologies that we have. What I do, the marketing guys tell me, I do enterprise threat detection through the science of behavioral analytics, and there's tons of buzzwords in there. So I catch bad guys with data and math. And that's a really fun job. It is really fun. So I'm going to start here. What do all these attacks have in common? No one probably recognizes this one, but I'm sure you've heard of JPMC. I'm sure you've heard of Walmart. I'm sure you've heard of Sony, and so on and so forth. And I could have added hundreds of more logos here. These are all very public data attacks. They were all cyber attacks. Data was stolen, credit cards, email accounts, and so on. What they all had in common were a couple of things. One is they were all examples of compromised accounts. At some point in the attack, someone's login and password was stolen, right? And so that's one thing that they all have in common. In fact, it turns out that over 90% of all cyber attacks as the result of compromised account. So someone that is logging in is Stephan, but it's not really Stephan. So that leads me to the second thing that they all have in common. They all could have been caught. Because if you had access to the right data, and you were smart enough, and you knew enough about me, you could be looking at this digital trail that I was leaving behind and say, you know what, that's not normal. It's not normal for this refrigeration vendor to be accessing credit card data. It's not normal for this person in HR to be accessing this section of the database, right? So these things were also all detectable. The problem is, this is actually a really hard thing to do, right? The problem can be thought of like this. It's kind of like an enterprise version of Where's Waldo, right? Because you have all these people in your company, you have all these machines, you have all these potential bad actors, and you're trying to find the one that's behaving differently. The way to think about it, though, is if you could somehow figure out what's normal for each and every single one of these employees, and if you could subtract out what's normal from each and one of them, then the difference between what that account is currently doing and what they normally do becomes really obvious. So imagine subtracting out the normal so the abnormal stands out, right? Does that make sense? OK, so that's really all it is, right? And again, I've simplified it a little bit, but this is something called anomaly detection, right? That's where you hear things like outliers, even though I hate that word. But the concept is you understand what's normal, you subtract away normal, and then the difference is abnormal. When that difference is big enough and dangerous enough, and I'll address false positives, but when it's big enough, then perhaps you should investigate. Now, I have simplified it a little bit now. It is really a hard problem to solve and do well. The good news is I'm going to give you 2 Kung Fu moves here today to let you solve it. So Kung Fu move number 1 is big data. I hate the word big. It's just data. I've been doing this long enough that I think big data is just data and analytics is just math. So Kung Fu move number 1, data, right? And I'm not talking about necessarily volume or the 4 V's and fast-moving data. What I mean to say is we have access to more data than we ever needed to or had access to in the past, right? So if you're looking for something that is related to a problem you're trying to solve, you probably have the data already, right? There's no extra processes now for you to go out to get new data. Chances are the data you need to solve your problem is already there. And that is actually really relevant in the case of security. The most complicated attacks in the world, still follow a playbook. And the playbook kind of looks like this. For those in security, this is the Manion attack lifecycle, and you'll recognize it. For those that do not, this is the way it works. Someone breaks into the system, typically through a compromised account, right? So some employee, unwilling victim of a spear phishing attack, clicks on that link, and all of a sudden, malware is installed on their system. It's key logging. It knows your password. You're done. By the way, average time for that to happen in your company is 1 minute, 22 seconds. It's not even a question now of whether or not someone's going to click on that link. It is an average of 1 minute and 22 seconds before that link gets clicked on. So chances are, if you're a company over a certain size, there's already compromised machines and accounts there. OK, so they're in. They establish a foothold. That means basically they're in the system. Then they start to escalate the privileges. Now that I'm in, what other passwords do I have access to? What other databases can I do? And then they start to do internal recon, and they move laterally. That basically means they're going from system to system to system, trying to identify other machines they can log on to. Which databases do they have access to? What tables in that database do they have access to? And then they maintain their presence. That means doing things like creating hidden accounts so that they can log in. If they happen to lose this account, or the guy wises up and changes the password, that's fine. They've got 5 other passwords they can use. OK, make sense? It's only at the very end in which they leave, right? It's only at the very end in which they get all those credit card records and start to upload it to the system. What do you think is the average time that the attacker spends inside your system before they start stealing stuff? Any guesses?
A month, days.
How about 240 days average? Oh. Average. And that's just of the ones that we know about, right? So it's probably lower than realistic. So that's why more data is so important. The standard approach basically only looks at your login records and network traffic, right? Firewall logs, right? And they're both really important. I'm not trying to say that's not a great place to start, right? But if you're only looking at suspicious logins, like, oh, this guy entered in the wrong password 3 times, that's a really small window of opportunity to catch the bad guy, right? So what do they have if they happen to log in because they spear phished? Network traffic, again, really small window, and it's too late, right? This is trying to catch stuff as it's leaving the building, right? So too late. So if you had access to SQL logs, right, which everyone does, right? Everyone's got a database. You've got SQL logs. You have an understanding of what users providing what queries in and out of that database. If you have access to application logs, you know what applications you're running. Then look at the coverage that you can get. Basically, the more data, the better and faster your detection is, in the case of cybersecurity. In the case of the problem that you're trying to solve, think about how better data that's closer to the problem can give you more accurate results. So that's Kung Fu move number 1. Kung Fu move number 2 really is the math. If you've seen some of this from IBM, I apologize. I was partially responsible for this. But this is kind of the traditional Davenport maturity model, right? So you see here in the gray, basically the standard types of technologies and math techniques you've heard about for a while now in advanced analytics. So everything from looking in the past, with standard BI practices, to looking in real time in the here and now, exactly what's happening now, to going into the future, starting to do some simulation from predictive to optimization. Now, there are 2 new pieces I've added to this maturity model. There's new data, and there's new methods. And there's almost been a renaissance of new mathematical techniques in the past, I'd say 5 to 8 years, that are really relevant in this new age, right? Basically, we have to deal with really, really messy data. And sometimes the data is not as rich as we would like it to be, OK? So that's where these methods come in. New data, I call it that because basically it allows you to take the columns of data that you have and add additional columns of information. Right? So take really, really skinny data sets because you get what you get and you'll get upset. Right? That's why I tell my daughter. So you only got 5 columns of data, but can you derive more meaning from those 5 columns? A good example is Twitter. Right? If you can look at everything a person has tweeted, there are models right now that can determine your age, your approximate age group, your gender, what country you live in, whether or not you have pets, and really narrow down to almost a socio-demographic group. And they can do that with 70% accuracy. And that is just with a single column of tweets, right? That's just socio-demographic annotation, related to the stuff that Watson does. So that's one part of it. There's also new methods. These are really good because, as you can see there, it's really good at dealing with really noisy data, right? There's a lot of dirt in data, right? You can't trust it all the time. Big difference between what I've got in my database versus what's coming in from Twitter, right? So there are techniques that we need to adapt to handle that sort of noise, right? So this is where we are today. So there's lots of room that we have to expand beyond the middle and take on these new methods. And that's just the cybersecurity. Right? So as you think about the types of techniques you can apply to your problem, there's actually a huge palette of stuff.
What's tokenization?
Tokenization is when you take bits of a language. Actually, a good example is Watson. Right? When Watson reads a medical dictionary, it basically tokenizes things into concepts. So here's a noun, and it's a part of the body. Here's a part of speech, and this is the word the, so it's just an article, so don't pay attention to it. So that's a concept, right? It's taking something and fitting it to an ontology. Okay. All right, so I get to talk about data science now, so this is great. So I actually have a very specific definition for data science, which actually comes from Drew Conway. So the way I like to think about it is effective data science actually does require industry knowledge, right? So you need, in fact, 3 things to pull it off effectively. One, you need hacking skills. Now, hacking in this case, unfortunately, it has nothing to do with cybersecurity hacking. We're talking here essentially about computer science skills. You need to know how to stand up a Hadoop system. You need to know how to code. You need to know how to make it scale. The second thing you need is math and stats, right? There really is some principled statistical methods that need to sit in the background. You can't just fake math, right? Because then you end up doing bad things, right? Everyone remembers when you were in high school and they taught you how to do statistics, and you're computing means and looking at p-values and counting standard deviations away. Right? So that's a class of stats called frequentist statistics. That stuff does not work on big data, right? Because everyone remembers they would tell you, oh, make sure you have n at least 20. You want a sample size of 20. We have way more than 20 now, right? So some of those techniques, they have to be updated. You have to do things right. But the third thing, you cannot ignore substantive expertise. Without the right use case and the domain knowledge, you don't have good data scientists. So there really is a Venn diagram here. If you are missing substantive expertise, then you're just doing machine learning, right? You're taking computer science, and you're taking a model, and you're trying to run a neural network. But it might be totally irrelevant to the problem at hand, right? You need this piece, right? But the other piece that you need is the math, right? If you don't have the math, then this is the worst place you can be, right? Because now you've got hacking and you've got expertise. So that's great. You have an idea of what problem you want to solve. You write a Python script. But without the right statistic applied in the background, then you could be led astray, right? And this is the one that scares me the most, because all of a sudden you've got an answer that came from a fancy model, but it could still be completely wrong, right? You got to get it right. Okay, so when I started in cybersecurity a couple years ago, I was both simultaneously excited and appalled at the level of analytics in cybersecurity. It was like in the dark ages, right? So this is something that came from Carnegie Mellon, the CERT team in 2011. Essentially, they specialize in looking at patterns of people that are insiders and how they steal information and take it out. So they came up with this rule. And the rule is, if the mail is from a departing insider and the message was sent in the last 30 days, and the recipient is not in the organization's domain, and the total bytes summed by day are more than a specified threshold, then send an alert. Okay? So the idea here is if someone's about to leave your company and you know it, then you should make sure they're not sending out more attachments than normal. Does that make sense? Right? Because it turns out that 75% of all internal thefts are from employees that have decided to leave. Right? So when someone gives notice, the security teams typically would try and do something like this to try and just make sure they're not doing anything untoward. Right? There are at least 2 things wrong with this. One thing that's wrong is this guy right here. Right? What's the right threshold? And the reason that's a tough question to answer is because the right threshold varies depending on who you are, right? If I'm in HR and I'm sending out resumes all the time, then my threshold of attachments should be way higher than someone who's maybe an engineer, and then they should never be sending out source code out, right? Does that make sense? So it's impossible to pick a single threshold that's going to work for everyone. The second problem with this, and we talked about it earlier, is actually this guy right here, send an alert, right? Two things. One, you could get a false positive, right? What if he just had an off day and he sent out a large zip file, right? But it was totally innocent, right? Then you get your false positives. The second thing is, by sending out alerts to your operator, you get alert fatigue, right? So somehow they have to manage to correlate volume of alerts with severity, right? So this doesn't work. So let's try and use right math to sort of solve these two problems. So one thing I want to do real quick for you is solve the problem of picking a threshold. And this is the way you can do it. It's really easy. So here are 4 different accounts, right? 4 pictures here. The bar charts represent me looking in the past and just drawing a little bar chart of how frequently they send out a certain number of attachments per day. Does that make sense? So this guy sends out lots of 1 attachments or no attachments typically, and then every once in a while sends more attachments, right? This guy always sends out no attachments or just a few number of attachments, and almost never sends out more than 1 attachment a day, right? So different distributions. Different people will have different bar charts, right? Once you've got these bar charts, you can do curve fitting. Everyone remember curve fitting in high school, right? You can fit it to a curve, and basically that'll tell you what normal looks like, right? And in stats, you can fit things to a bell curve, a Gaussian curve. A gamma curve kind of looks like a tilted. Anyway, it doesn't matter. It's a really good curve to fit it to. It nicely gives you a good approximation of what normal looks like. Once you know what normal looks like, you can actually predict what abnormal looks like, right? So that's what I've done here in the red curve. So you can use Bayes' law to compute what abnormal looks like. And you can see, as you would expect, if this guy sends out this many attachments in a single day, that's not totally unusual, right? In fact, it happens about 20% of the time. However, if that same number of attachments went out from this account, then that is really abnormal. Does that make sense? So this is nice. Now I don't have a rule that either fires or does not fire. Now I have a way of taking every single event and computing a number that represents how weird it is. This is 20% weird. This is 80% weird. With me so far? Cool. All right. So let's talk about false positives. Let's suppose that we just saw an account access an unusual important network share. Okay? And you touched it, and we say, OK, that's weird. It's a 25. Okay? That one behavior could be really important, but it could also be a false positive, right? Maybe he just changed job roles within the same company. So it's OK for him to be touching this network share for the first time, right? But suppose we just saw his account also do it at a time of day he was never active at before. And take from a source code project that no one else had been touching for months. And copy those source code files to a USB drive, and so on and so forth. Do you see what I'm having here? Your intuition should be that the more of these improbable events happen at the same time to the same account, the less this starts to feel like a false positive, and the more this account feels like something that's really important for you to investigate, right? So that's really the general principle. What you want is not to have just a single predictive model. You need to have multiple predictive models that are each being able to measure the granularity of how certain you are. And the more of these you can compound together, the more and more certain you can be that you've got something that's really important that you should pay attention to. It's not going to totally eliminate false positives. Nothing ever will. But you can greatly, greatly reduce the occurrence of that, okay, with the right combination of models. Okay? All right. This really works. It is amazing. So I've been doing this for a couple of years now. We have 30 to 40 customers, everything from intelligence agencies protecting our country's secrets with our software to cancer companies, drug companies protecting their drugs, with our software. This is probably my favorite story. So this is a semiconductor manufacturer based out of the States. And they became aware of 2 of their engineers that stole IP from them. Specifically, they stole source code. Okay? They didn't want that to ever happen again. So they worked with a very large security vendor, not us, obviously. But they spent a year and $1 million, couldn't quite get it to work. We deployed 12 models on that same data source. And as you can see here, not only did we find the same 2 engineers that they knew about, which of course they did not tell us about in advance, but we surfaced 11 additional names. Some of these accounts in China, by the way, were taking as many as 17 million files inside a single day. It was a really big exfil. Okay? So, data and math, right? So, Here's what the data looked like. This is literally the data that we got. It was a single file. It looked like this. How can we possibly do this? So what do we have here? We had a timestamp column, so we knew when things happened. We had the user account. This is the engineer name. Now, to some of the earlier points, this is scrambled. That's why it doesn't look like John Smith, right? Math works perfectly fine on scrambled data, so everything can be anonymized. That's the beauty of it. So these are the developer names. This is the IP address the developer came from. Next two columns, pretty interesting. This is what the developer just did in source code. So they diffed, they synced, they checked in, they checked out the action, right? And then this is the file and folder name that they touched. Again, these are just strings, so we can just anonymize them. So we have no clue who these guys are or what they were touching, but we knew when and what they just did. You would think that with a skinny set of 5 columns, there wouldn't be very much we could do in terms of predictive models on it. But we actually built over 20 probabilistic threat models to look for suspicious behaviors. And I'm not going to list all 20 here, but I want to inspire you by thinking about the 4 categories of models that we did. We had a lot of fun naming these. So sneaking is when you do something that's out of pattern. So like 2 a.m. on a Sunday. You've never done that before. Hoarding is very interesting in the security context. That's when you're taking more than a lot of stuff in a short period of time. So that's hoarding. You can also be taking small bits of stuff over a long period of time. Security guys call that low and slow. So you're trying to defeat some threshold-based system. Okay? Mooching is a fun one. It turns out that for many content repositories, the ratio of how much you contribute to that repository versus how much you take for that repository, what we call mooching, that's a very predictable ratio, right? So someone typically checks in a certain amount of files and then checks out a certain amount of files, right? That ratio would be different for a software engineer than for someone that's a product manager and he just checks out files and builds. Does that make sense? So when we see changes in mooching, that can be indicative of someone else different that is now stealing a large amount of stuff from it. So that's mooching. Wandering is when you're touching pieces of source code in this case, or database tables that we did not expect, right? So the refrigerator vendor taking credit card stuff. So that's wandering. Right? So now I'm going to show you exactly. So hang on to your hats. Here's where the math comes. So I'm going to show you 2 of the 20 models and exactly how to implement it. Again, just to show you that it's actually not that hard. Okay? So let's suppose we want to figure out when someone is doing something at an unusual time. Okay? Now, if you're someone's buddy, right, and they know when you come into work and when you take a lunch break, you could always ask the human, right? But the problem here is there's too many people, right? So we can't ask the human. So let's see if we can build an algorithm to do that. So what you have here are the 24 hours of the day. That's on the x-axis, right? And I want you to imagine every time we see an engineer do something, draw a little tick. Okay, so you see this guy comes in around 8:30, tick, 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 tick. Doesn't do anything during lunch because it takes a lunch break, right? Makes sense. Tick, 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 goes home, must work at Interset because comes right back to work at 8 o'clock, works almost until midnight. Good, solid developer. That's what we want. Now, every time you draw a tick, I want you to imagine dropping a little grain of sand, right? So what happens is you build up the sand structure where the more commonly we see them at a particular time of day, the higher the pile of sand gets, right? Okay, this is something called kernel density estimation, right? All we're doing here is instead of dropping grains of sand, we're dropping little bell curves, right? And the bell curves kind of add up a certain way. So what I can draw here is basically a nice curve that looks like this that tells me the probability of that individual being active at any one particular time, right? This guy, if I see him do something at 10, that's perfectly normal. But if I see this account do something at 2 in the morning, that is really weird. He's never there. Okay? It's amazing how much of a fingerprint this is. Here are 2 random engineers that I took from this data set, from the semiconductor company. And you can see they're completely different. In this case, I stretch it out so I can see the entire days of the week, right? 7 ticks on the x-axis. Engineer number 1, this person deserves a raise. He is working, or she, probably she's working 6 days a week. Right? Never come, like look at the height of the curve for Saturday. It is almost as high as the regular days of the week, right? A great person. You can see that they do take lunch breaks, but they almost, like it's not predictable, all right? This is in total contrast to engineer number 2. By the way, we found out later engineer number 2 is a contractor, and it kind of shows 9 to 5, okay? Monday to Friday, never comes in on the weekends, always takes a lunch break. It is amazing how much a fingerprint this can be, right? It's a very scalable, super straightforward model to build, okay? So now what we can do is anytime we see an activity at a time of day, we can compute a number that tells me how weird it is, okay?
He only bills by the week, obviously.
Yeah, it's, yeah, it must be a fixed size contract. Yeah, Thursdays is a good day for this guy. Actually, I think it was because Fridays was the end of a sprint, so he needed to check everything in for the Friday meeting. But anyway, all right. So let me show you something a bit fancier. So again, same data set. Remember that really skinny data set? Okay. So what you can do is you can cluster for activity patterns, right? Clustering is a way in which you can group things that are similar together mathematically. So what you're seeing here are a bunch of dots joined together with lines. The dots represent source code projects, right? It's not unusual for a large company to have multiple folders or multiple instances of source code. If you've got a large database, think about all the different tables that you have, right? So you've got the IP, you're splitting up into pieces. The lines connecting the dots represent different developers. So that might be a little bit backwards than what you're expecting. Keep it in your head. Developers are lines, you'll be OK. The length of the line is related to how normal it is for that developer to touch those two source code projects. Tracking with me? So what that means is that when we group things together, the clumps represent common patterns of access across different source code projects by the developers. And what ends up coming out of the math are 4 clusters. These 4 clusters ended up corresponding to 4 different software teams inside this company. You can see a fairly small team in the purple up there that's made up of only 2 source code projects. On the other hand, here's a fairly large team in the green that's made up of 22 source code projects. Now look how nicely packed and separated those balls are. That is actually really good, right? That means that you've got a really predictable model, right? There's almost no overlap in these things, even in this 2D projection. So in other words, because it's so tightly packed, if I'm a developer on product green, then it is perfectly normal for me to be accessing any other green source code project, right? Because they're all connected together. Short lines. However, if I'm a developer on product green, and I reach out and I take source code from project red, then that is abnormal. And that's what this guy did. So lines are developers. This developer was on project green. He or she did take source code from project red. He did it at 2 in the morning, and we've never saw him do anything at 2 in the morning before. And he took 16,000 files inside a single hour. So 3 models drove his individual score to the top of the list. And that's how he caught one of the 11. OK, make sense? All right, I am almost done. So in conclusion, there really are 2 kung fu moves, right? Big data analytics, when you break it down, it's really just data and math. But you gotta have the right data, and you gotta have the right math. So when you are thinking about the problem that you are trying to solve, I want you to think of 2 things. One, I want you to think about the right data. What would you give a human to do, to look at? You know, assuming he had infinite time and infinite skills and a team of size infinity, what would you ask him to look at to try and solve your problem? That's the right data set. The second thing is, if you did have that infinite team of skilled guys or girls, how would you ask them to solve the problem? And they might use words like, in the cybersecurity space, well, I saw this here, and that looks weird. Or I'd look for this, and because I know this, and this number is higher than what I expected, then I've come to this conclusion. When humans use words like that, those are all words that can be translated into stats. They really can, right? And that's where your statistician can come in. But it's got to be driven by the use case, and it's got to be implemented in the right way. That's it. I'm done. Super easy. Go and change the world. Thank you.
I just noticed we misspelled your name.
It's OK.